It's not funny. I don't know why I decided, hey, let's wait on the elevator, because I'm not going to run up 8 flights of stairs, but it's the elevator in the back room.
Oh,
so
that
for like
was
15 seconds, I'm like, damn it! Had to go to the math department.
I'm not sure I've ever seen that elevator work.
I'm pretty proud of myself though. I made it to like the 7th floor, like booking it. By the end of the 7th floor, I was like, oh my god, no, just a little further, no. Like crawling out now, that last flight of stairs took longer than the first 7. I walked back, I ain't gonna lie, I couldn't run back, I walked back to Jhevon. Because, yeah. Well, I think I earned the right to skip leg day. I'm probably the first person on planet Earth that has done that. Most people just skip it. I've earned the right to skip leg day. Let's continue. Let's get through this. I think we still have enough time to finish the important material. I wanted to jump into the bonus material, but we'll probably do that for tomorrow. We're going to continue with induction. So, plan for today, do some more examples on regular induction. We're going to also talk specifically about a technique that I actually used when proving that the world order principle was equivalent to mathematical induction, and that is proof by minimum counterexample. And then we're going to bolster induction by practicing the strong form of induction. There are many forms of induction. We'll cover these. We're covering 3 types basically. For those of you who go on to doing something like set theory, you'll learn about things like transfinite induction and things like that. But we're covering these 3. Where our set that keeps track of all our statements is the natural numbers. Sometimes we want to keep track of statements with much larger sets than the natural numbers. So we're going to look at techniques that allow us to do that. Let's make sure we're on the same page. Recap, induction. What does it say? The principle of mathematical induction.
P1 is true.
Well, how does it start?
For a given relationship, P of X.
Yeah, remember back in calculus when you would have like a theorem and it will tell you blah, 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 then it'll give you an equation, and then blah, 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 and you ignored all the blah, blah, blahs, and you just memorized the equation, and like, yeah, this is cool, I'll just memorize the equation, because he's only going to ask me to compute something. Those days are gone, all right? Now, when you remember something, you need to remember everything. The sentence that came before the equation, sentence that comes after the equation. How does induction start? What kind of statements does it help us with? Let P of n be a statement. Any statement?
True statement.
Depending on n.
That depends on n. Where does n live?
Natural numbers.
Right, so this is a statement that talks about, it's making some claim about some statement that involves n, where n is a natural number. And ultimately the goal is we want to prove that this statement will be true no matter which natural number you plug in. It will be true for all the natural numbers. So you want to prove an infinite number of cases all at once. Obviously we can't do that, so we apply the principle of mathematical induction, which says if there are 2 requirements that we have to check, which are?
Base case.
Right, there's P of 1 is true. This is called the base case, or the base step, or something similar to that. What's the second thing we have to show?
K plus 1.
If P of k is true, then pk plus 1 holds for some particular k. So for some specific k, this must be true. Then there's a conclusion that says P of n is true for all n. So prove it's true for the first first guy, whenever it's true for some random guy, it'll be true for the next guy. And this tells you that it's ultimately true for everyone. So that's basically induction. And we prove that that's the case using the well-ordered principle as an axiom. So let's do some more examples. We actually did a few. Let's do some more here. Let's extend one of De Morgan's laws. So we're going to say let Pn.
Professor?
Yeah.
I have a question. Number 2, right?
Yeah.
Does that not open for all k? Maybe it's just like a matter
No,
of-
for some k.
But
To assume it holds for all k would be begging the question.
but
No,
We
no.
want to conclude that it holds for all.
No, what I'm saying is that, say that in the case that you have P of 1 true, but the P of 5 is true, for like how can you conclude from like P2, P3, P4?
Part 2 allows you to conclude for that. If it's true for some particular guy that you pick, it will be true for the next guy. So to prove that it's true for P5, all you have to do is, well, P of 1 is true, and if P of 1 is true, P of 2 is true, P of 2 is true, P of 3 is true, P of 3 is true, P of 4 is true, P of 4 is true, P of 5 is true. So you can stop at 5, which is the one we care about.
So you're saying just like an arbitrary k then?
An arbitrary k. It's some specific, you fix some k. And it doesn't matter where this k lives, you just want to prove it. If it works for some guy, it will work for the next guy. And then you prove it works for the first guy, which automatically means it works for everyone after that. The strong form will take more into account here, and we'll see that when we get to it. So P of n is the statement that A1, I don't remember which law I extended, but it's going to be similar. Intersect A2. If I take the complement of the intersection of a finite number of sets, it will be equal to, what do you expect it to be equal to?
union,
The union of
the complement.
the complements individually. Okay, so step 1. We're going to do the proof. What do you want to prove here?
P1.
So P of 1 is it true that the complement of this is actually equal to the complement of that? Is true. So P of 1 holds. Assume P of k holds for some k. That is if I take the intersection of k sets, that will be the union of the complements of those k sets. We show P of k plus 1 is true. What is the statement P of k plus 1 here? What do we need to prove is true?
PK plus 1.
Yeah, but what is that statement?
The intersection of A1 through A sub k plus 1 log.
So that's what we need to show ultimately. Now we can't just state that that will be taking the question. We have to prove that this is the case. Ideas? ideas here. Anyone? Yeah?
Well, since we're assuming PK holds, can we use
Yeah, this is true.
Can we use that to somehow narrow down?
Yeah, how? What does this guy remind us of?
Coefficient?
No, the entire thing, the entire equation. What does it remind you of?
De Morgan.
De Morgan's law? Do you know what De Morgan's law said? Tell me the De Morgan's law you're talking about.
I'm not sure, I just know that I think it's related to De Morgan's.
Okay.
Can I take that one?
That is a law you should know, by the way. De Morgan's law, two statements in De Morgan's, whether it applies to sets or logical statements, you should know what those statements are.
Can I take that left-hand side and unite it with an extra guide? In red.
First, tell me what this says.
The complement of A union
Okay, so if I take A union B, take the complement,
B is going to be A complement intersect B complement.
and the second statement,
The complement of A intersect B is A complement union B complement.
obviously, this is the one that we would apply here. Can you think of a way to apply that to this? Yeah?
Can we make A sub 1 intersect all the way to AK? The union of A sub 1 to A sub K, can we make that one set? And then have that union with,
So this guy here,
yeah.
let's call it some other set. Let's call it A. Now what? Well, now we have the intersection of two sets, which I know holds by De Morgan's law. This is equal to this guy union that guy by De Morgan's. And this guy is equal to this guy by inductive hypothesis. Right? We assume that for up to k things, the statement holds. So the bar above these k things, which I replace A to represent the k things, this statement can apply. And it turns out now that I have the union of the k plus 1 things. So pk plus 1 holds. Plane holds for induction. So, odds are if something has a name, you're going to want to remember it, right? This isn't just some random theorem 3.6 where, okay, who's going to remember that number? No, they gave it a name, De Morgan. It's named after someone. You usually want to remember things like that. Right? They have like a name that's in English, that's not some number that's numbered by the section. Okay? And that allows you, whenever you're in a similar situation, right, that's a part of what math is about, using the fact that you know solutions to simpler problems to build on them to get solutions to more complicated problems. Okay? So knowing, guys, that little things like this will help you with larger issues. Sometimes things extend naturally and you can use something that you know works in a smaller context to show something works in a bigger context. Let's do another. Let's do an example with divisions. Prove this statement. 7 divides this expression. Proof. First step.
Base case.
Base case. If I take 3 to the 4 times 1 plus 1 minus 5 to the 2 times 1 minus 1, this is equal to, well, that's 3 to the 5th minus 5. What's 3 to the 5th? Huh?
243.
243 minus 5. That would give us what? 238. Is that divisible by 7?
Yeah.
7 goes into this part 3 times, remainder 2. 7 goes into 28 4 times. So this is 7 times 34. Which means that 7 divides 3 to the 4 times 1 plus 1 minus 5 to the 2 times 1 minus 1, which means that P of 1 goes. Right, so remember the symbol divides means that this expression is a multiple of that integer. So now we take our hypothesis, pretend this holds for some k. Assume 7 divides 3 to the 4k plus 1 minus 5 to the 2k minus 1. We show p of k plus 1 holds. And you can write this just to make sure you don't state it as a fact, because you'd be begging the question. That is, you want to show that 7 will divide when you plug in k plus 1 here. So that would be 3 to the k, 4k plus 5, minus k plus 1 here, 5 to the 2k plus 1. Right? That's what we need to show. Ideas?
I'm sorry, where did you get the 4k plus 5 and 2k plus 1?
I remember pk plus 1 is the same. I want to show that the statement holds when I replace k with k plus 1. So if I go here and I plug in k plus 1, here I plug in k plus 1, the 4 distributes. This is 4k plus 4 plus 1. And then 2k plus 2 minus 1.
Oh, okay, thank you.
I distribute. Right? Now I can't make that statement. This is what I need to show. So I can't start there, but I can start here. This is true. Which that notation itself is kind of tricky to deal with, so what would we do here? Probably
Can we do like, since we know 7 by 7, if we 3 to the 4k plus 1 minus 5 to 2k minus 1 is equal to 7 times, let's say the number, L.
7 times some integer. Right, so let's say 7L, where L is an integer. Okay.
Can you move the 5 to k minus 1 and then you multiply by 3 or 2 and
move this over and then multiply by 3 to the 4th.
yeah, no, I think we need more stuff though. And then we'll multiply that by 5 squared again. And then
But then-
I don't know if that would look nice.
Yeah, but then you'd have to add this, you'd have to subtract this guy from both sides. Will we be able to get somewhere with that? You're thinking along the right lines, I think. You do want to somehow use the fact that we have this, but we want to make things look this way. One way, especially if it's not clear here, is to rather than just try to multiply your way out, maybe try to do a substitution in the sense that, can you write this guy in terms of that guy?
3 to 4k.
This is 3 to the 4k plus
times
1 times
3 to the 4.
3 to the 4. This guy would be 5 to the 2k minus 1 times
5 squared.
5 squared. So let's actually just do a direct substitution. So I know, for example, that 3 to the 4k plus 1. And there'll be many algebra tricks that you can use here, but this, I find, is one of the more straightforward ones. You can try to get your other one to work, but I think it's going to be issues like having to subtract that 5 to 2k plus 1. Anyway, we know that this is true. And so let's actually substitute that into this expression and ultimately show that we can write that as 7 times something. So then, if I take this 3 to the 4k plus 5 minus 5 to the 2k plus 1, this is actually 3 to the 4k plus 1 times 3 to the 4 minus 5 to the 2k plus 1. This is equal to I'm going to substitute this in here. This part here, I'm going to replace it with this expression. Now this is already a factor of 7, so I'm hoping that when I multiply out, I'll get something else that's a factor of 7. Let's actually see what that gives us. What would that give us here? So I would have 3 to the 4 times 5 to the 2k minus 1 plus 3 to the 4 times 7l minus 5 2k plus 1. Which I can rewrite as this guy, because I want to, as much as possible, get the things that I know about in the process. So it's 5 to the 2k minus 1 times 5 squared. This guy here is not a problem. He already has a factor of 7. These guys don't have any obvious factor of 7, so let's do with those separately. So this is 3 to the 4th times 7L. Just put this guy up front and send him along. Plus, here I have a common factor of 5 to the 2k minus 1. And that will leave me with 3 to the 4th minus 5 squared. And what's 3 to the 4th? Is that 81?
81.
And 25? 81 minus 25? 56. Can we get a 7 out of that?
Yep.
Great, I'm glad to hear. I hate everything.
Yeah.
So that would be 7 times
8.
8. And so ultimately now I can write this as 7 times 3 to the 4 L plus 8 times 5 to the 2k minus 1. And this is an integer. Which means seven divides 4k plus 5 minus 5 to the 2k plus 1. I.e. p of k plus 1 plus.
Do we have to put like the following by P and I equal whatever, or why?
You can, well, ultimately everything after this step we did was algebra. But you can say that, you can mention a sentence here that this applies. You can say this by inductive step. But other than that, I think the algorithm speaks for itself at this point. Right? The fact that you can say this is equal to that, therefore this guy equals this, which you substitute. Let's do some more induction. But regular induction is what your test is up to. So we'll talk about minimum counterexample and strong form, but technically you don't have to know it. So let's do a couple more examples on this. Because it's one principle, but like I said, the problems can vary widely. So you have to kind of get used to applying the same principle with a wide array of problems. So here's another statement. So you remember those complaints, some of you have probably made it yourselves, back in calculus 1, calculus 3, where you're like, oh, he gave us the test and it was nothing like what he taught, nothing like the homework. Looking back, you know that's not true. Calculus, you're not going to it looks exactly like the homework. It looks exactly like what was done in class. Calculus isn't that different. No matter what example they pick, if it's at the Cal 1 level, it will look like something you've done before. Here, that is a valid criticism. You can go to an exam and see problems that look nothing like what you've done before, and it's fair here. It's actually fair. So while criticism is valid, it's actually something you will be expected to be able to do. You have to understand a concept and be able to apply that to a variety of things. And the best way to do that is to just look at a variety of things and try to finagle your way through them. Eventually you'll build a sort of intuition as to what can work, what can't work. But you'll realize that, again, all those little tricks that you learned from before with algebra and factoring stuff and simplifying things, or maybe applying some other smaller theorem, like the Morgan's law to a bigger thing. Like all those things come into play. You can pull knowledge from anywhere. That's kind of where we want you to get to at this point. So yeah, I can give you an induction problem. It won't look like any of these that we're practicing, but that's fair. You should just know these are the steps that I need to get through. I need to figure out how to get through them logically. Once I show these two things I'm done, let's move on. So let's actually through this. First thing. What's the first thing?
P is 0.
Base, yeah. Because the
Base. You can put a little sentence if you want to look all fancy. We employ mathematical induction, or we'll use induction on him, or something. Just the easier reader into the thing. Like the higher you get, the less courteous people get. But at this point, they can say, "Oh, we're going to do this. Oh, we're going to do a proof by contradiction. Let's assume the contrapositive." They'll say things like that to you. But in the future, they'll just start the proof, and you're supposed to pick up, "Oh, this is what they're doing." But at that point, you'll be so familiar with what the different proof techniques are that you can pick up what the proof is using just by what the first sentence says. But here you can introduce what you're attempting. Okay, so the base case would be, well, 3 to the 1 is greater than 1, i.e. P of 1 is true. Great, so that was just me plugging in the first thing. Okay, so now let's do the hypothesis. Assume 3 to the k is bigger than k for some k in n. We need to show that 3 to the k plus 1, the statement must hold if I replace k with k plus 1. How would we go about doing that?
Multiply both sides by 3.
Yeah, seems to make sense. 3 to the k plus 1 is just 3 times this, right? So we know 3 to the k is bigger than k. This would mean if I multiply both sides by 3, the inequality will stay the same. This means that 3 to the k plus 1 is bigger than 3k. Which means this is equal to k plus k plus k. Right? This has to be bigger than or equal to k plus 1 plus 1. K is a natural number, so 1 is the smallest possible value. So this is going to be greater than or equal to what its smallest possible value is. This is of course equal to k plus 2, which is definitely bigger than k plus 1. So I ultimately showed that this guy is bigger than that guy, and that's pk plus 1. And you can end it right there. Or you can easier read out of it. Oh, this means the claim holds by mathematical induction. Wasn't too bad. How about throwing an in square root? saying we can do induction on n, which is a little bit of foreshadowing there. For those of you who are going on to higher mathematics, there will be times where your statements depend on several integers, and you kind of want to focus induction on only one of them. So sometimes an induction proof will state specifically which one of the integers we're doing induction with, and the other one should fall in line. But 2 to the 1 is greater than 1 squared, which is equal to 1. So with 1 rules, hypothesis. Assume 2 to the k is greater than k squared for some k. Then let's try a similar trick to what we did here. Then that means 2 to the k plus 1 is greater than 2k squared. Where do we go from there? In fact, where do we need to get to? What do we need to show?
So k plus
2 to the k plus 1 is greater than
k plus 1
k plus 1 all squared, which we might flush that out. So ultimately, I want to be able to say, make that statement.
Plus, can we then go off and prove that 2k squared would be greater than the drawn out k squared plus 2k plus 1? For
How would we do that?
Oh, sorry, is okay.
Well, that's the case. So ultimately, I would need to show this, right? That this part holds. Right, so I have the k squared there. I need to get that 2k plus 1 to be true.
Can you make that k squared k times k?
Okay.
Then you got k squared plus k times 1. I mean plus, no.
Well, I'm sorry, is k integers or natural
Yeah, k are natural numbers.
well, can we say that for any given k squared is greater than or equal to 2k?
That's what we want to show. Is that true?
Can we show that by further induction? Like induction within the induction? For one, it would be one, oh no, let me,
Induction on k. You could do that. There are times when you have to do that. There are a variety of ways you can do things here. Is it always true though? It turns out it's not always true. So what are you going to do with that? This is kind of a segue into the need for a strong form induction, if that's a hint to you. Here's the thing. Note. K is at least 3. I'd be able to say this. K squared plus k times k is greater than or equal to k squared plus 3k 2k plus k, which is greater than or equal to k squared plus 2k plus 1 equals that. And what I'm putting in blue is sort of going to hint at you why the other forms of induction we're going to use can be very helpful, right? So in the case that I can justify this fact, which is not always true, right? It's true for anything that's bigger than 3, actually, right? Now, once you're at least 3, there are multitudes of ways you can prove that. You can even use calculus if you want, right? The derivative of this is going to be greater than the derivative of that all the time, once you're past that point. But getting to that point is going to be an issue. So one thing we can do is, you know what, if this is bigger than 3, this will hold. So let's actually show that it is true for up to 3, right? So I know it's true for 1. Is it actually true for 2? What would k equals 2 say? I mean, 2 to the 2. Well, that means 2 to the 3 would be greater than
2.
Should it be greater than or equal to the problem?
Yeah, I think that should be greater than or equal to. Huh?
Shouldn't it be greater than or equal to?
Because that would be where k equals 2, and for k equals 3, what do we have here? We have 2 to the 4th would be greater than or equal to. If I plug in k equals 3, what would I get?
8. Oh, 16. Wait, but then the original claim is false. Isn't it always going to be false for...
Do you have the right statement here?
I don't think so.
Because for n,
For K2,
Because then you have 8 is greater than or equal to 9.
for K2, should it not have been 2 squared is greater than or equal to 2 squared?
Yeah.
am I looking at the right statement here? 2 to the n, 2 squared is greater than or equal to 2 squared. And if I plug in 3,
Greater than or equal to.
oh, I'm multiplying by, I'm looking at the wrong thing. I was looking at this step when I should be looking at that one. Right, this is the statement I want to prove for all k. Right? Now, if my k is at least 3, it's definitely true. So I want to verify this directly for k up to 3, which means I need to plug in here. I was looking over here. So plugging in here.
Oh, that's where the 3.
Right, this is the statement we need to prove, right? The statement is true if k is at least 3, so we need to verify this for k up to 3. It was in blue, I was reading the wrong first.
Okay,
So if k was,
Can't the claim be disproven though? when you plug in n equals 3. Because then it says 8 is greater than or equal to 9.
This is why reading is important. It's actually not for all n. That's true. That's what the mistake was.
All n minus.
It actually gave us a limit on n. I'll just add it here. That was
Okay.
add that scribble smaller. See the importance of reading and paying attention? Okay, so this is sort of a generalized form of induction, where our base case is not the 1. The base case was actually at 5. So here we have 2 to the 5th compared to 5 squared, which is 25. 2 to the 5th is 32, that holds. And I think even with that, this we don't even need the equal sign. And means, at this point, we know that that guy is at least 5. So that's even nicer. Okay, so the base case was 5, so change that. This would be the same, this would be the same, this would be the same. But now I know that k is at least 5, so I actually don't need an extra. So you can cross those two lines out. And so we would have 2 to the k plus 1 is greater than 2 k squared, which is equal to this, which is greater than 5 of these guys. Which I can split into this, which is at least, this is at least 15. And that's definitely bigger than when you have 1. Yeah, sorry about that. That was a little technical. So. You might hear people say this, but they might not. Generalized induction. Meaning you want to adopt the induction, but you want to shift to where your base case occurs, and you can actually prove that this will work equivalently. You can prove that that will work equivalently. It's not going to be that bad. You basically go to the induction theorem and just write each integer as that integer minus the k for whatever base case you want. So I put that example there to show you that the base case doesn't necessarily have to be 1 specifically, but it can be any starting point you want. So all you have to do is prove that it's true for the first guy in the line, and it will be true for, and then if it's true for any guy after that, it will hold forever. And that's the last example on induction. So that's pretty much what you're responsible for on Thursday. Right, and the homework will have a wider variety of this. As far as the test, I I think I mentioned this, I posted a review on some problems, that the solutions aren't live yet because I don't want people relying on the solutions as a crutch. So I'll either make the solutions live tonight or maybe or even early tomorrow, because I really want you guys to go and actually try them on your own without having the temptation of looking at the answers. Because you'll get in trouble when you look at the answer for something. Because when you have someone presents a logical argument to you, you're going to read it and you're like, yeah, that makes sense. And you're going to understand the answer, and you're going to fool yourself into thinking that means you understand. It's super easy to do that. So I don't want you to fall in that trap. And again, from calculus, we know that that's a trap, right? People will be like, when I'm in class, I understand everything that happens on the board. I don't understand how I went on the test. Well, that's exactly what happened. You understand what I did on the board, not what you did. Right? So it's very important that you really attempt it yourself. Give it a serious attempt, because it's going to be very, very difficult otherwise. So, but I did mention the format. It's going to be about 5 problems. And I'm not going to ask you any stupid problems like, oh, what's the definition of this, or do the truth table. Like, we're beyond that. They're all going to be proof problems. I'm going to ask you to prove a statement in each of these problems. One of which is on new material. New material in the sense that I'm going to introduce a concept to you in the exam, give you, hey, this is a definition of a concept, prove this about that concept. Okay? So you might want to even look at that, some problems like that from random places in the book, anywhere you see that there's a short example, maybe look at that as well. So you will be able to use old techniques on this, so it's not like you really need to know any new concepts to deal with this new material. You'll be able to use old concepts to prove it. So I might introduce this new material and you realize, oh, I can actually prove this fact about it using induction this way. Or I might be able to prove this fact about it using contradiction for that, or something like that. So that's going to be it. It's up to induction. Right, so up to what we did just now. Okay, including perhaps generalized induction, which is the base case might shift on you, but that will be fine. Once you notice you don't miss that typo, you'll be fine. I'll also include bonus material. To reward people who are going ahead. Let's say you're really killing it and you listened to me on the first day and you didn't bite off more than you can chew, and you're only taking this one class and nothing else is going on for your life and you really want to kill it. You want to go ahead. I might ask you some problems on chapter 7 and 8. Chapter 8 is going to be a super important chapter, so you might want to look over that if you have the time. I'd rather spend the time with you really killing it with chapters 1 through 6 and really understanding them. But if you have a few extra time, a couple extra hours, and you really feel comfortable on the material up to chapter 6, you can look into maybe like chapter 8 and look at the basic definitions there, try to be familiar with it, maybe read through some examples, maybe try a small proof on it. Chapter 7 is a chapter that is about prove or disprove. So again, it's not really us learning anything new. It's just, it's a chapter about, let's say a statement is out there, you don't know if it's true or false. How would you figure out, first of all, how do you choose to think or believe whether it's true or false, and then prove that or disprove it. And so again, that's using old techniques. But it's just, again, it's a case where you're not told beforehand that this thing you're proving is true. They just throw out a statement, and you have to use some intuition to figure out if it's true or not. And then chapter 8 is where we start talking about equivalence relations. Learn about what a relation is, what an equivalence relation is, what equivalence classes are. And that's a pretty important chapter.
Will the bonus questions also be like similar points, or
Come in.
how many questions are the bonus questions? How many points will they be?
I don't remember. It'll be like a variety of short, small problems, but it'll be something like in the regular test, it's like 100 points, and that's the maximum. And the bonus section will maybe be 20 points. I'll ask you like 4 questions, 5 points each, 4 small questions, or like 5 questions, 4 points each, or something like that. And you try to grab as many as you can. And as long as you complete this, you're allowed to do that, and you can get extra points on it. But yeah, so 5 proof problems. It's going to eventually hit all the techniques. You need to know how to prove things directly. Proof by contrapositive, proof by contradiction, proof by mathematical induction, how to prove if and only if statements if they occur, and just general proof writing is what you're going to need. As I said, at least 4 problems will be on familiar topics, although I can't say they'll be on, so things like divisibility, whether things are odd or even, that kind of stuff. But it's still, the problem itself might look slightly different to what you're doing. Some of them are pretty much the same like we've been doing in class. Some of them will require you to think a little more and maybe simplify things in a different way. But that's basically what it's going to look like. You're going to have the entire test period, the entire class period to do that. So you'll have an hour and 40 minutes to basically get through 5 problems. If you're daring, try to complete 6 problems.
So when you say 5 problems, you mean just 5 proofs?
Yeah, 5 proofs. Prove this statement. Right. And one of them is going to be, here's a definition, prove this about the definition. Or prove this about elements in that definition. Yeah, so it's just like 5 proofs. Yeah.
What are we allowed to assume? Like, say that you give some sort of question with like rapid 3, rapid 2, can I immediately say that that's irrational because I don't have a problem or something like that?
Yeah.
Do I? Okay.
Yeah, facts about algebra, arithmetic, you can assume those. You can't assume, basically you can't assume anything that it's really kind of unknowable. Like if you end up with a radical of 2n, you can't tell me that's a perfect square without justifying that. Like what is n? That, you know? But yeah, if you have square root of 9, you're allowed to say, oh yeah, that's 3. that's not going to change. Yeah.
So, oh yeah, so I noticed in the homework for chapter 5, at one point they wanted us, like it says hints, prove that if 3 divides a, then 3 divides a squared. But that's Euclid's lemma. So on the exam, we can just use lemmas and theorems that we know, right?
Yeah.
If I just say,
if we prove the theorem in class,
what about if it's online? If I say, oh, by Euclid's lemma or by something,
that's fine, especially if it has a name.
Yeah.
If it has a name, you can use it.
Okay, thanks. I want to prove that.
And there are some things that even if we've shown it in class, you're allowed to use it. Like we've shown, I think we've mentioned this several times. Like x squared is even if and only if x is even. Right? See, he even finished the sentence before I even finished it. Because so something like that you can say, right? We've shown this. Right?
That was so awesome. I don't have examples going on for like 20 minutes, but like for example, like I know a lot of the last homework involved irrational, or chapter 5 involved irrational and irrationals.
Mm-hmm.
And a lot of the times I just use like the sum of 2 irrational numbers won't be rational. Just in the proof. That would be fine, right?
Yeah.
Oh, given that.
Yeah, like how numbers combine.
Given that they're not equal to 0, the sum.
Yeah, how numbers combine you can use. Like you'd be able to assume, okay, if I add 2 evens, it's an even. If I multiply an even by an odd,
Oh,
it's
I
an
guess
even.
that would just be arithmetic.
Yeah, that's arithmetic. Yeah, so that's the situation. Let's branch off into a new idea. We've actually seen it before. Proof by minimum counterexample. This is the technique. Proving by using the well-ordering principle. That's the theorem that says any subset of the natural numbers has a least element to obtain a contradiction. Now it's pretty much, this proof was used when I was proving that the well-ordering principle is equivalent to mathematical induction. Remember, I created all a set that would contain all the integers for which P of n was false, and then I used a proof by contradiction to show that that set had to be empty, which means that it was true for all of them. You're going to do the same kind of principle here. You're going to go through the proof of mathematical induction. At some point, you're going to stop and you're going to say, well, if this is false somewhere, then there must be a smallest guy for which it's false. So you're going to assume that, hey, here's this guy for which it's false, and then you're going to prove that, oh, that's going to make a contradiction, and so there is no guy for which it's false. So that's basically what a proof by minimum counterexample is. So remember, a counterexample is an example used to disprove a claim. So basically you say, if we attempt to disprove it, we're going to get in trouble, we're going to get a contradiction. Right, so give me an example that would disprove it, and that gives you a contradiction, so it has to be true. So you're using a proof by contradiction inside of an induction proof, and the well-ordered principle is the method you're using to do that. Whenever you do that, that's called a proof by minimum contradiction. So let's give an example of that. Start out pretty easy here. Two to the 2n minus 1 for all n. Proof. We start out with induction. We want to verify P of 1. So if I take 2 to the 2 times 1 minus 1, that is equal to 3, which is equal to 3 times 1, which means that 3 divides 2 to the 2 times 1 minus 1. And so P of 1 goes. Assume P of k holds for some k. We show P of k plus 1 holds. That is, we show that 3 divides 2 to the 2k plus 2 minus 1. So you want to go ahead and do that. So here's how we can employ the proof by minimum counterexample. Assume to the contrary that this does not hold. So given that this holds, let's assume for the sake of contradiction that this does not hold. Then, there is a smallest number for which it doesn't hold. And you can even put it in here if you want, though you don't have to, by the well-ordered principle. Right? If there are a set of natural numbers for which it's false, that set must have a least element. Right? That's the well-ordered principle. So we pretend it's false to obtain a contradiction. If it's false, there's going to be a smallest guy for which it's false. That's going to be our minimum counterexample. We have to show that this leads to a contradiction. Right? It can't, this guy can't exist. Okay. Well, what would that mean? So this kind of requires some scratch work. I mean, this kind of proof, if you took a Calc 1 class in which you had to prove limits using the epsilon delta definition, you'd be familiar with this kind of proof. If you've not, you will be familiar with this kind of proof when you take Advanced Calculus 1. But there are some times where a proof where you have to go to the side and you have to actually work it out. And then you come back and write the proof like you knew all along what the answer was. There's that kind of thing. So for now, this is kind of scratch work. I'm going to write in a different thing. Right? We're going to, ultimately we're going to want to say is that this means that 2 to the 2k plus 2 minus 1 is either equal to 3l plus 1 or 3l plus 2. Now, what would I want to say here? So we want to try to find a guy for which this is definitely going to be true, right? Where I'm going to be able to write this as 3 times some integer. Okay? So what we want to do is we want to start plugging in some k values, starting from the lowest k value and start to work our way up and see if we can get to a contradiction. So we know it's actually true for k equals, let's figure out some value that is true for. If we have k equals 1, what would that give us? By the way, that would mean that k plus 1 is at least 2. And so, what would that mean? What would that mean if k plus 1 is at least 2?
2 to the 4 is equal to 3m.
Come again?
2 to the 4 is that can we
Does
also-
that work?
Well,
Yeah, of course.
That actually works, right?
Yeah.
That's 15, which is 3 times 5. Right? So it seems like the first guy allows it to actually give us a contradiction right away to this guy. Now, sometimes you're not that lucky for it to work on the first guy. Sometimes the first guy actually gives you something that does not work, and so you bump it up, you bump it up, you bump it up, until the point where you actually get to a value for which it's not going to work. So we know that in this case, it's definitely going to work. So how do I work that in then? Now let's work that into a proof. So you go, this is you do to the side, you scribble it to the side. And you can say something like, set m equals k plus 1. Right, so I kind of want to get the fact that it works for the next step here. Since if k equals 1, the claim holds, our counterexample must be larger than that. Our counterexample does not occur at k equals 1. So k plus 1 must be at least 2 for the counterexample. Then, if you have 2 to the n minus 1, this would be equal to 2 to the k plus 1 minus 1. Which is going to be, do you see how we're going to get divisible by 3 here? So I'm assuming n is the smallest guy for which it does not work. I set m to be k plus 1. I know k plus 1 has to be greater than 2.
So k equals 1. Yeah.
How would I get the fact that that is 3 times something?
K plus 1 is 2. I think that's it.
Come again? And remember, we can use our induction thing.
Could we substitute k plus 1 for m and then just have them both on the same side? So like 2 to the k plus 1.
2 to the,
Never mind.
ultimately I want to show that this is divisible by 3. How do you go about showing that that is a multiple of 3? And by the way, you can assume that 2 to the 2k minus 1 is equal to 3 to the k.
We could.
Yes, that's pk. Alright, pk is that this claim holds for some k. Right? We need to show that it holds for k plus 1, which is we need to prove this statement, which is to say that 2 to the 2k plus 2 minus 1 is equal to 3. So I can assume this at any point. I need to prove this, and I want to prove this using contradiction. Contradiction is going to say, suppose it's not true for someone, there must be a smallest guy, I'm calling him m. I set my m to k plus 1, and so I want to show that this guy must be divisible by 3, assuming that this holds.
Can we say something about 2 to the k plus 1 and split it in such a way that 2 to the 2, 2 to the 2. I'm saying maybe like 2 to the k times 2, but I don't think that gets us anywhere.
And then,
Put it in the three. You just
Then
substitute
that's
the
2k.
and then substitute what?
the 2 to the k minus 1.
Be careful.
Wait.
This is just multiplying the 2 to the k, not the minus 1.
Wait, then isn't it 2 times 2 to the k is just 2 to 2k?
No, it's the k plus 1.
No, that would be 2 to the k.
We're trying.
This would
Well,
be
we know this. What about substituting this? Do you think that'll work out here?
You can find a value for 2 to k.
Well, they're equivalent given k equals 1. So we already proved.
I think the book rewrites M in terms of the counterexample using it based on K.
Yeah. So how do I apply that here? I want to show that. Oh wait, do I have the right statement here? There is some minimum n for which it works. That's why you're having trouble substituting. The minimum n. So this would be 2m plus 2. 2 times k plus 1 plus 2. This would be speed 2 to the 2k plus 4. Which I can write as 2 to the 4 times 2 to the 2k minus 1.
Oh, now we can substitute that for 3.
And now you can substitute what for 3k?
2 times 2 to the k minus 1 for
2 to the 2k.
Yes.
That's not fair. Do you see it now?
But how do you, could you make 2 to the 2k equal to 3k plus 1?
Right. That's what I'm just solve for the 2 to the 2k. This is equal to 2 to the 4 times 3k plus 1 minus 1 by inductive hypothesis. Where do we go from there? Well, this would give us 3k times 2 to the 4 plus 2 to the 4 minus 1.
You get 24k minus or plus 7, but then you have the
Right.
minus 1.
This guy ends up being the fact that we know that works for here.
3. Just 15.
That's just 15. Which it's not always like after the first step you get that. Sometimes you have to do it for several steps. So this would be here 15, and you can factor right through from that. Two to the 4k plus 5. This means that 3 divides 2 to the 2n plus 2 plus 1, and that gives us controversial.
So, Professor?
Yes.
Just to be fair, you kind of, I'm oversimplifying it, but are you doing something along the lines of like, assume that it doesn't work, let me show you why it would work anyway?
Yeah, because that's a contradiction. We assumed it does not work.
But
Right,
then,
so I assume there's some integer that I can plug in here where the 3 is not going to divide it.
But then would you have to show that it's a contradiction for both forms? Like, would you have to then show for 3L plus 2 as well, or once you show for 1?
What do you mean 3L plus 2? Where?
If 3 does not divide, then you have that it can be in the form 3L plus 1 or 3L plus 2?
Yeah.
Would you have to show it for both, or after showing 1 are you fine?
If you can show for 1, it's fine.
Oh,
Because this guy, which I assume could not be written as a multiple of 3, ends up being that. It ends up being a multiple of 3. Now, it turns out there might be, and I'll do some more examples of this next time. It might be the case that after one cycle, it doesn't work. Where what you would do is you keep going to see how far you can push it. Then what you'd have to do is you'd have to prove that it works for each of those with specific numbers, and then show, well, if it's not going to work, it's going to work for someone bigger than that, and then you can introduce that case where you finally see it working out. I'll show you an example of that next time where it's going to take. I'll show you an example where it takes us like 2 steps, and then an example where it takes us like 6. But that's basically the idea. So this is one iteration. I think your textbook did this problem or something very similar, but I'll show you more beefy problems next time. Technically, it's not something you need to know for the test, but it's segueing into how we can expand on our induction. So we have homework today. So homework 5, be sure to leave it here. Homework 6 is not due tomorrow, but you can start practicing. Not all of it.
Oh, really? Only 6.1 or no? Only like 6.1?
I'm gonna do like some way.
I don't know.
It's okay.
But there'll be, in the homework set, there'll be a set that says induction, there'll be a set that says minimum counterexample, because it's in type.
Yeah. So it's only.
So I would practice the parts that you will
So
practice.
it's only.
Yeah, the test stops there. So technically this isn't on the test.
We'll have so much time.
So you can practice ahead of time. But you don't need to submit.
I don't know if Mark's